Boom. All right. So like I said, I said that I would talk about division by zero, but I didn't get into it last week. And I want to, touch on that right now. So when we're talking about dividing by zero, some students will get confused and they'll think that I'm talking about zero divided by a number. Can anybody tell me what, for instance, zero divided by 25 is? This is not a trick question. I don't think it is.
Zero.
Yeah, right. It's sort of like multiplication in the sense that like whenever we're dealing with zero, when we're multiplying, a number times zero is going to be zero. Um, but whenever we have zero divided by a number, you can think about it like, imagine that you had 0 slices of pizza, or you had 0 pizzas, and you wanted to divide it up into 25 pieces. Well, if you took 0 pizzas and you divided it up, well, you would still have nothing, right? Um, well, that sort of makes intuitive sense, and you can use lots of other analogies here. If I had 0 cookies and I shared them with 25 friends, each of them would get 0 cookies because I had nothing to share. Um, but a lot of students will then say, okay, well, let's pose a different question. Let's do 25 divided by 0. What should this be? Now, this one is not a trick question, I don't think, but it's a little bit trickier to think about. You don't want to automatically assume that it's going to be the same answer.
25.
You think it's what?
25.
25. Okay. Let's think about that. If I had 25 pizzas and I divided them among 0 friends, is that how you're thinking about it? You would still have 25 pizzas? Okay. Yeah, and that's where the analogy sort of breaks down, because we really want to think about this division problem like this. 25 over 0. And whenever mathematicians write a fraction like this, it's a division problem. But when we have, let's say, a over b, mathematicians think about division in terms of multiplication. So what this is telling you is that if a over b is equal to some number, let's call it x, then, so like if this is true, if a divided by b is equal to x, then what I can do is take x times b and get a. And I know that this might seem confusing until I give you like a concrete example with actual numbers in there and not variables, but this is just saying that multiplication and division are opposites of each other, right? Like if I had 25 divided by 5, we know that equals 5. Okay, so if I have this statement, this also implies that this number, 5 times this number times 5, is equal to this number on top. So this times this equals this, and I definitely won't be using this highlighter anymore because it's a little hard to see. So that's how we want to think about the problem. So let's go back to this example that I'm talking about here, 25 divided by 0, and think about that in terms of this new definition of division. Okay, so 25 divided by 0, if it equals 1, right? And I'm not saying that it does equal 1, so let me put a little question mark here. If it equals 1, then that implies that 1 times 0 is equal to 25. But is this true? Well, that's definitely not true. 1 times 0 is going to be 0. So we have a problem here. Somehow. Can anybody think about, okay, let me say that this is not true. So let's think about 25 by 0, 25 divided by 0 is equal to some number, x. And that has to imply that some number times 0 equals 25, right? By that definition that I've given you. What does this number have to be? Can anybody think of a number that would multiply by 0 and give you 25?
Nothing.
Nothing. There is no number that you can multiply by 0 and get 25. So that's the reason why we say you can't divide by 0. Because if these two statements are linked to each other by definition, and you can't find a number that makes this true, then we say instead that a number divided by 0 is undefined. That there exists no number that can be divided by 0. So you just have to be careful because when we have these examples, like 0 divided by negative 97, and we compare that to negative 97 divided by 0, these are not the same. And you want to be very careful with that and not just be on autopilot and say that, oh, this one's 0. Oh, this one is 0 too. Okay, because that's not the case. This one implies that, like, we can solve this one because if we think about this in terms of what it implies, that let's say, okay, if we want to solve this for x, for whatever this missing number is, right, then 0 divided by negative 97 equals some number implies that some number times negative 97 is equal to 0. Now, in this situation, can you think of this number x that will make this statement equal 0? Any number.
0.
0. 0 is a number. It is a quantity. Sometimes we are a little bit lazy in our speech and we say that 0 means nothing, but 0 is a number. So in this instance, x could be 0, because if you plug 0 in right there, you would get a true statement that 0 times negative 97 does in fact give you 0. So 0 divided by a number is going to be 0 all the time. So we can put it that way. 0 divided by a number is always 0. But if you have it reversed, a number divided by 0, we say this is undefined. Any questions or comments there? Okay. Okay. Well, that was just a little brief detour back into the world of division, just to be very clear that you cannot divide by 0 if you have a number divided by 0 that's undefined. But today we're really going to be talking about algebraic expressions. We've been working with numerical expressions, that is, these mathematical statements that have numbers and operations, but algebraic expressions these things combine numbers and variables with mathematical or arithmetic operations. And these expressions can be simplified and manipulated the way you would manipulate numbers, but they cannot be evaluated unless you're given values for the variables. So until given values for the variables. Okay. So in these kinds of expressions, let me just give you an example algebraic expression, something really simple like 2a plus 3. Okay. And let me label some of these things. So in this expression, we have one operation, the operation of addition, and we have these two quantities. One of them is just the number 3. So in this expression, the number 3 here, we're going to call a specific term, we're going to call a constant, because this value will not change because the number 3 is fixed. It is constant. Okay. But this value over here, this quantity, its value can change because it depends on what the variable's value is. So we call this a variable term. Let me call this a constant term. And I call this a variable term. And what do I mean by the variable term can change? What I mean is that if I told you, let's imagine, or let's say that a is equal to 3, then this expression will change and I can evaluate it and say I have 2a, so 2 times 3 plus 3. And now I can evaluate it. That is, I can solve this math problem with my order of operations and say, okay, I'm going to do the multiplication first. So 2 times 3 is 6. And then add 3 to that. And so when I evaluate it, I'll get 9. So I can substitute this value into the expression, this variable value, and then use my order of operations to simplify this down so I have a single value at the end. But I can say, okay, let's imagine that a is a different value. Let's say -5. Well, if that's the case now, then I go back to the original expression and I plug in this new value for my variable term. So I'll write 2 times -5 plus 3, and now I have to simplify this expression. So I'll use my order of operations to say 2 times -5 is -10, and then I'll add 3 to that. And if I have -$10 in the bank and I deposit $3, I'm still going to be in the negative. I'll have -7. Now, this is the usefulness about algebraic expressions, is that we can use this variable term as a placeholder that can change depending on the scenario. But the constant term, that value is fixed and it won't change because it's not attached to a variable. And that's exactly why they call them variables, right? When we say things that vary in life or there's variation in life, we say that things change, right? So this variable term will change based on the value of that we assign to the letter A. Variables tend to be symbols like letters. X is one of the sort of favorite symbols or variables that we use in mathematics, but it can be any English letter. Does that make sense? Or are there any questions? Okay. When you have an algebraic expression, let me give you another example. Negative 2x plus 25. Okay. You should be able to identify which one is the variable term and which one is the constant term. So if I looked at this, I would say, okay, this guy doesn't have a letter attached to it, so I know that that's a fixed constant term. And we'll just call it a constant. For the variable term over here, that's the thing that's attached to the letter. We can label this as the variable term. And the variable term has two parts. And I sort of used this fact but didn't explain it, and I want to explain it now. The two parts of the variable term are this -2 that's in front of the variable, that's in front of the letter, and what you don't see in between them is some sort of operation. But the implied operation is -2 times whatever the variable is, whatever the number that we're going to assign to the variable. So that we can say that this expression implied multiplication. So when you don't see an operation between a number and a variable, the default operation is multiplication. And this might seem weird. It might seem like overly complicated, but really you deal with this stuff in your everyday life. So imagine we bought 5 apples. You might on your grocery list, I don't know that anybody does this nowadays, like make a grocery list and then figure out what the prices of those groceries are so that you can total up what you think your bill is going to be at the checkout counter. I think that this is something that people did, maybe back in the day, but not so much anymore. If you're living on a prayer, like some people, including myself, you might do this, plan out how much you're going to spend on groceries and stuff like that. So it might not be uncommon, but anyway, you would write, okay, I have 5 apples on my grocery list. How much do apples cost? Okay, maybe apples cost $1 a piece. They're big apples. Let's say that they're Fuji apples. Well, you could write a statement on your list that says, I need 5 apples. But if you're feeling particularly lazy, you could just say that 5A, right? You've made a code for yourself. I know I'm going to get 5 apples. And then if you know that each apple costs $1, that's the same thing as saying that A is equal to 1. And so if you wanted to find the cost of buying those 5 apples, you would just plug in and multiply, right? 5 times 1 is equal to 5. So that's going to be your total bill. But if you go to the grocery store later on, and now apples cost 50 cents a piece, well, you have this expression that you want 5 apples, and now the prices change, right? So we can substitute in that different value for the variable and say, okay, well, we're going to do 5 times 50 cents. So 2 of these would be $1, 4 of them would be $2, and then we'd have $2.50 here for our total bill. For the 5 apples. Does that make sense? So you're already sort of using variables in your life. But, we don't want to sort of, we're going to complicate it a little bit, but that's the core of it. That's why mathematicians use letters for variables, because now if we're talking about different kinds of quantities, imagine that I just, I don't only want apples. I want apples and oranges and bananas and gallons of milk, right? Then I'll call those different quantities different names. I might say, okay, at the store, I need 2 apples, 3 oranges, 5 bunches of bananas, or maybe 5 little bananas, I don't know. Okay, and so on. I have a grocery list. Well, I can make if I'm lazy and I'm not feeling like writing the words out, I might say, okay, I need 2A plus 3O. And I put a little curly on it so I don't confuse it with 0. Plus 5B. And then that's our mathematical expression now. I have 2 apples plus 3 oranges plus 5 bananas. And I can now figure out, go into the newspaper, find the ads for HEB, figure out how much apples cost. Let's say that apples cost 50 cents. Let's say that oranges cost, these are really big oranges, so let's give them a cost of 75. So we might say O is equal to 75 cents. And then the bananas, I don't know, let's say they're $1 a piece. Well, now I can plug those values into this expression and then figure out what my total bill is supposed to be. So 2 times 50 cents here is going to give me a whole dollar. 3 times 75 cents is going to be, I don't know, let's get the calculator out. 3 times 75, just because I'm feeling a little lazy, that's going to be 225 plus 5 times $1 is going to be 5. So I have 6, 8, 25. There's my bill. Does that make sense? I'm just trying to attach real life value to these esoteric math things that we do, right? There's a reason for the madness. And notice that in this expression, we have 1, 2, 3 terms that correspond to different quantities: 2 apples, 3 oranges, 5 bananas. So there's 3 different variables. And notice that I didn't add these together because an apple doesn't cost the same as an orange. It's a different kind of quantity. So I can't add 2A to 3O. Not the same price, not the same thing. Right? So these quantities have to be the same thing. So for instance, let's say I'm shopping and I pick 4 apples. And then I remember that maybe I have a guest staying with me and they like apples too. And so maybe I want to pick up a couple more apples for them. Then I pick up 2 more apples. Well, if we want to turn this into a mathematical expression, we could say I had 4 apples and then I pick up or add 2 apples to my cart. Well, how many apples should I have?
6.
Yeah, 6 apples. So when we add variable terms, as long as they're the same kind of term, the same kind of quantity, I can add those together and just attach that variable to them because we're only talking about apples here. But if I had my guest, let's say my guest likes oranges. So I pick up the 4 apples for me because I'm an apple fiend. Maybe I'm gonna make a small apple cobbler. And I pick up 2 oranges for them. Can I add these together and say that I have 6 apples?
No.
No. So what we say then is that we can only combine like terms. In life, you might say we can only compare apples to apples. We can't compare apples to oranges. So we wouldn't be able to do this. Okay. So if I gave you the expression, for example, let's not talk about supermarket or grocery stores right now. I guess it's on the mind because I need to go get groceries. But anyway, if I gave you the expression 2x plus 4y minus 3y plus 7x, can anybody simplify this?
Nine X and 7Y.
Why 7y?
Oh, maybe not. Maybe it's 1Y, my bad.
Yeah, you got
Because I
it.
was adding them together.
Yeah. So that's exactly right. So if I told you to simplify this expression, I haven't given you any values for the variable. But what we can say is I have two of these quantities that I'm calling x. You can think of it like I have two apples. So I like to circle them and give them the same shape because I have the same object, 2x plus 7x. Well, if I want to simplify that, like if you were talking to a friend, you wouldn't tell them I have 2 apples and 7 apples. You would just tell them one number. You would say that I have 9 apples or 9 of these objects that we're going to call x. Similarly, if you had 4 oranges and then you gave away or ate 3 oranges, well, how many oranges would you have left? You would have 1 orange left over. So we have one of these objects called y that we have left over. Okay, but mathematicians are a little bit picky here. I said at the beginning of this that when we have a number next to a variable, that's implied multiplication. And we call this number the coefficient. The coefficient on the y is 1, which means this says 1 times y. What is 1 times any number?
That number.
It's whatever that number is, right? 1 times 25 is 25. 1 times negative 10 is negative 10. So the same is going to be true if we have a number like 1 times a variable. It doesn't matter how much these bananas cost or how much these oranges cost. 1 times whatever the cost is going to be whatever that quantity is. So instead of writing a 1 here, I'm just going to simplify this a little bit further and say we have 9x plus y. And that the difference here is very minute. These are the same quantity. We just don't want to show this 1. And you can think about it like we have 9 apples and 1 orange. But if I told you that I had 9 apples and an orange, wouldn't that mean the same thing? So that's an analogy that you can use to say, like, that's why we don't want to put the 1 in front of it, because you would still understand if I said I have 9 apples and an orange. I didn't say a number for the orange, but you understood that it's a 1. Okay. So algebraic expressions are super useful in mathematics when you're dealing with different kinds of quantities that their values can change. And so there's one property in arithmetic that I think is going to be super valuable for you guys, and that's the distributive. If I could spell distributive property. And this property says that if I have a number times, let's say b plus c. that this is going to be equal to whatever A times B is plus whatever A times C is. And we call it the distributive property because it's like whatever this number here is on the outside of the parentheses, you're distributing it and multiplying it by each of the quantities inside the parentheses. This works the same if you had subtraction. So if I have a number and I'm multiplying it by B minus C, whatever those numbers are, I would have A times B still. And this symbol in the middle would be subtraction still. And I would have A times C because I'm taking this number on the outside and it's like I'm distributing it and multiplying it by both the B and the C. And this is a way that some of you guys might already be doing mental math in your head. For instance, if I asked you what is 5 times 77 without writing it down. Without writing it down, some of you guys might say to yourself in your head, well, I can say that 77 is the same thing as 70 plus 7. And then in my head, I know I'm writing it down, but you might say in your head that this should be 350 plus 35 because I can do that multiplication. And then at the end of it, you add them together and you get 385. You know, that was a weird looking 5. I'm going to be self-conscious about that all day. And then you can check that in the calculator to make sure that, you know, that works out. 5 times 77 is 385. But doing the mental math, you might break up that 77 and then multiply things that are a little bit easier to multiply and then add the results.
Is that how you want us to do it?
No.
Okay.
But the reason why I bring this up is because when we're talking about variables in the mix, if I had an expression like 5 times x plus 3, and I told you to simplify this, you would need to use the distributive property to multiply 5 times x and 5 times 3. And so you would simplify this down to 5 times x is like saying if I have let's say x represents apples. I'm going to the store and I want an apple for myself, but maybe there are 5 people that I need to cater to. So how many apples should I get? Well, that's 5 times 1 apple would be 5 apples. So I need 5x. And then I don't know, something costs $3. Let's not worry about what that $3 is. 5 times 3 is 15. So we would say that this is simplified using the distributive property. Okay, so let me give you guys some examples. Distribute and simplify. Um, 6 times x plus 9, negative 2 times 6x plus 6y, 7 times 5x plus 7y minus 8. And then maybe the fourth one will be 8 times 2x minus 5 plus 3x. Okay. So I want you guys to work on these, but I'm going to throw you guys into breakout rooms so that you can talk it out amongst your peers. Okay. And we'll work on these for the next 5 to 10 minutes. So let me go ahead and make this breakout rooms. And we want to create 3 breakout rooms and go ahead and accept the invite. You should see some sort of a notification in the Zoom panel. Once I open all the rooms, I mean. There we go. How's it going over here?
It's going.
You guys have any questions for me?
The third question, oh, never mind, I see it. Okay, I wrote it wrong.
Okay.
7
Any other questions?
minus 8. I don't think so.
Okay. I'm gonna go and jump into another room, see if there is anybody who has needs some help. So I'll be back to check on you guys in a bit.
Okay.
Hey, how's it going over here?
It's going. I guess we have a question for number 2.
Okay.
Regarding whether we're supposed to drop the plus sign because it's 12x And is it plus negative 12y? Or can we just drop the plus sign and be minus 12y?
Yeah, so like if you add a negative quantity, if you have plus negative 12, it's just simpler to say minus 12.
Okay,
Yeah,
Okay.
good question.
thank you.
You got it. I'm going to jump into one of the other breakout rooms. Hey, do you guys have any questions for me?
Yeah, on number 2,
Okay.
we had negative 12x plus, and then do you put the negative 6y like in parentheses?
Well,
Does
shouldn't
negative-
that also be negative 12?
Right, negative 12. Oh, I'm sorry. Yes, negative 12. I'm sorry.
Yeah, so that's a common mistake. I just wanted to sort of catch you on it. Like where students will distribute and multiply this by the number in front by the first one, but then they'll forget to multiply that by the second one. So just make sure you catch yourself for that. But anyway, to answer your question, if you have negative 12y and you have plus negative 12, well, if I give you a negative quantity, it's just easier to say subtract. So instead of plus negative 12y, you would just say minus 12y.
So it'd be a negative 12x minus 12y.
Yes.
Okay.
Yeah, because we sort of don't want to complicate our lives too much by having, stacking up our operations, because then it looks confusing. Okay, do you guys have any other questions?
I think we got the other ones.
Okay, I'm going to jump into one of the other breakout rooms now and see
Okay.
how they're doing. All right, guys, how's it going over here?
I think I got them all answered.
Okay. Anybody else need any help with that? With any of these? All right. Let's go ahead and join the main room. Okay, so hopefully we were able to get through those. It seemed like everybody was able to figure out that distributive property. It was pretty straightforward, right? So for this first problem, we're just going to distribute or multiply the 6 by these two quantities, x and 9. So we should be getting 6x plus 54. For a negative number, what I like to do is, just so you don't lose that negative sign, I go ahead and circle this before I draw these little arrows. And you're just multiplying negative 2 times 6x. So that's going to be, you're just multiplying really the coefficients, the numbers in the front. So that's going to be negative 12x. And negative 2 times 6y, positive, this is a negative times a positive. So it's easier to just say that's going to be a negative 2 times 6y is going to be 12y. So when you read this result, you would just say it negative 12x minus 12y. Okay, did anybody run into any issues there? You could write x, negative 12x plus negative 12y, but having a plus and a minus sign next to each other is just too complicated. So we'll just drop the plus and call it a negative, or just call it minus. Students get confused about the difference between the negative sign and the minus sign, especially since calculators have a different subtraction symbol from their negative symbol. But mathematicians, when you write down problems, we understand that you could interpret this as minus, or you could interpret it as adding a negative. They both mean the same thing. So it's just simpler to write it as having only one operation between them. You could distribute across more than one term, or more than two terms, sorry. So we'll take that 7 and multiply it by each of these terms. And this should simplify to, 35x plus 49y minus 7 times 8. Oh, Lord. 7 times 7 is 49, and then I add another 7 to it, so that should be 56. Right? Then finally, if we want to simplify this expression, this fourth one, we have to do the multiplication first. So because the distributive property is like multiplication, it will come before the addition. So I can't add 2x plus 3x because addition comes after the multiplication. So let me distribute or multiply this out first. And that will give me 16x minus 40 plus 3x. And then I can simplify by adding up or combining my like terms. So the 16x plus 3x. Well, if I had 16 apples and I add 3 apples to that, I should have 19 apples minus 40. Again, this is like apples and oranges. If I have a variable and a constant term, they're not the same kind of quantity. So I can't add these together and call it 59 because I don't know what the value of x is. So this value is going to change depending on what x is. So I don't want to be mixing my apples and oranges. So I'll just simplify it and call it this. Any questions? Cool. All right. Do you guys feel like you need a 5-minute break?
We can always use a break.
Yes.
Okay, so let's just take 5 to 10 minutes to just get some water, walk around, stretch, come back, and at about, let's call it 1:43.
Thanks.
You guys got it.
Sure.
Okay. I just realized that there's absolutely no way of me being able to tell whether you guys have come back, but I figured we'll just give it a minute to see if there's anybody that is maybe dawdling a little bit as we return back to just some of the last topics that I wanted to cover for this lecture. Did anybody have any questions about what we've covered up to this point? I know that as an instructor, sometimes students will just blurt out in the middle of a lecture like, why do we need to learn all this? Like, is this going to be on the test? That's me acting as a student, right? And we find it a little bit rude. We're taken aback because, like, I understand and sympathize with that feeling. Like, oh, I need to figure out what I need to do, like the bare minimum that I have to learn to pass the test. But you know, it might seem like some of these things are a little bit long-winded, my explanations, but trust me, if you're really genuinely trying to listen to what I'm saying and understand what I'm saying, it will give you a richer understanding of the more complicated things that we're going to get into. Right now, it feels a little bit like a buffet where I'm giving you this piece, I'm giving you that piece, but it's all going to come together in a complex symphony. And just like I said last week, that this is going to be a little bit like Mr. Miyagi teaching Daniel karate. I'm giving you the tools and the perspective that you're going to need so that when we get to the things that are arguably more complicated, you'll realize that you've learned karate all along. You've been learning karate all along. You've been learning algebra all along. So up to this point in the lecture, do you guys have any questions for me? Things that you found a little bit confusing, but maybe I was going too quickly through it that you just want me to like revisit real quick? Well, if we have no questions, then we're gonna jump right back into it. So I touched on this briefly, and I've been performing this idea throughout this lecture, but there's a difference between simplifying and evaluating algebraic expressions. When we simplify things, what we're really doing is, one, we distribute using the distributive property if possible. Sometimes you don't have to in a particular problem. And then after you're done distributing, you combine like terms. That is, you do the addition and subtraction. So that's how I think about it, actually. I think of, in terms of simplifying these algebraic expressions, order of operations through GEMDAS is always going to be on the table. That is the rule, the law of the land. But the distributive property is like doing your multiplication first. Multiplication. And combining like terms is like doing your addition and subtraction. It's just that we use this terminology now, distribute and combine like terms, when we're talking about expressions that have variables in them. Write subtraction down here. There we go. So if you were given the instructions, for instance, to simplify, and let me give you an example that's pretty good. Let's say that you had a weird looking expression that said 7x plus 5x. All of that was over 4. And then we had to subtract from that 2 times x plus 5. I'm sorry, x plus 1. this expression looks pretty intimidating if you're not used to seeing something like this. But we're just going to use our order of operations to simplify what we can, and then we'll worry about evaluating it later. So I said that order of operations is the law of the land, so I'm going to go ahead and write down what I need to do here. I need to use GEMDAS. Okay, so I asked myself, do I have any grouping symbols? And I have some grouping symbols here. I have this stuff in parentheses, but I have x plus 1, and since this is a variable, I can't add that together. I can't add x plus 1 because this is like apples and oranges. Since they're not like terms, I can't combine them. So I'm going to move on. I'm going to say, okay, are there any other grouping symbols? Now, when we introduced GEMDAS, I said grouping symbols could be parentheses or it could be fraction bars. And we can take care of this stuff on top of the fraction and on the bottom of the fraction if we have expressions above and below the fraction bar. So in some sense, we could say that this is a grouping symbol here, and I can simplify this expression since I have 7 apples plus 5 apples. We're just calling apples x for now. So I could rewrite this and call it, let me give myself a little bit of space so that it's not all bunched up. 7 plus 5 is going to be 12x divided by 4. And then this thing over here, I couldn't add these quantities together before. But if I write this down as -2 times x plus 1, just rewriting that phrase, and I look at this, well, I've done my grouping symbols. I've done the stuff inside the grouping symbols. I don't have any exponents, so I can move on from that. Is there any multiplication or division? Because remember, these are like the same priority. Well, a fraction is sort of like division, and distributing is sort of like multiplication. So we can just do that from left to right. And here I have 12x divided by 4, and you might be tempted to think that because I have a variable term divided by a constant term that I can't do that. But here we're going to use the simple analogy that I had 12 apples and I'm dividing it among 4 friends. How many apples should they get? Well,
3.
3. They get 3 apples. So 12x divided by 4 is 3x. Okay, then I can move on and do my multiplication over here. And I'm going to go ahead and circle the number that's in front of the parentheses, including this symbol. Now I said there's sort of a duality between the negative sign and the minus sign. So when I distribute, I'm going to treat this as a -2. And then I'm going to multiply that here and here. So now I can call this -2x or -2x. And then -2 times 1 is -2. Okay, is that crazy to anybody? Okay, and then at the end of the day, we can say, okay, let's clean up this space. Can we simplify it any further? I have 3 apples, and then I get rid of 2 apples or put them back on the shelf, and then subtract 2 oranges. Well, these are apples, so instead of saying I had 3 apples and I got rid of 2 apples, I can just say I currently have 1 apple or an apple. Okay, so you could put the 1 there as a sort of a helpful guide, but if we really wanted to simplify it, we could just say 3 minus 2 is 1, but 1 times x is just x, so let's leave it at x. And I'm just going to bring the -2 down, and this is simplified. Does anybody have any questions about this thing?
Yes, I have a question.
Sure.
I understand that the 12x we divided in 4.
Yeah.
Divided by 4. So why can we not do the same with the number 2? It is the number 2 minus 2 is different as a dividing 4 that doesn't have any variable. Do you understand my question? I'm sorry.
Yeah, I think I understand what you're saying. You're saying, okay, I have a variable term up here and I'm dividing it by a constant.
Exactly.
But I said that you can't combine a variable and a constant before, right?
Yeah.
Correct. It turns out that through multiplication and division, you can have a number interact with a variable, right? Like I said, I'm gonna buy, let's say I have a recipe, a small recipe for apple cobbler, and it calls for 3 apples. If I wanted to double that recipe calls for 3 apples, and I want to double 3 apples, I could just multiply the 3 apples by 2 by a number, right? And I would have 6 apples.
So only multiplication and division can do it, but
not addition or subtraction.
And subtraction, no. Okay.
Yeah, like I couldn't take this and call it 1 minus 2 because this is a different kind of quantity.
Okay. Thank you.
Yeah, so when you're distributing, when you're multiplying or dividing, you can have a single number interact with a variable. But when it comes to combining like terms, that is addition or subtraction, you have to keep them separate. You can only combine like terms through addition and subtraction. Okay.
Okay, thank you.
Good question. Okay. Well, there's another kind of operation that I want to introduce here that you might have seen already in the homework for R2 part 1, and that is absolute value. So I'm going to sort of tell you a little story about absolute value, what it means, and we're going to go back to the number line to think about this. So let me draw a number line. I know that I can throw 0 in the middle if I want. I know all the positive numbers are on the right side of 0, so this would be like 1, 2, 3, 4, and so on. And then all my negative numbers are going to be on the left side, -1, -2, -3, -4, and so on, all the way to negative infinity. And if you went all the way to the right, you go to positive infinity. Okay. Now, negative and positive numbers are really nice when you're adding and subtracting them. Well, let's stay in the realm of addition. So if I'm adding 2 numbers, let's say I added 3 to -3. What should 3 plus -3 be?
0.
0. Now, I don't want you to make the mistake of thinking that this should be 6 or -6, right? It turns out that the idea of addition is like walking around on the number line. So I'm either sliding to the left or sliding to the right. 2 hops this time. Okay, that's just a joke. Got to throw them in every now and then when I can get them. But we call these 2 numbers opposites, or we call them additive inverses. Let me go ahead and throw that fancy term here. Additive inverse, which just means the same thing as opposites. They have the opposite value. And they're on the opposite side of 0 on the number line, right? Like if I put a little dashed line here, if I were walking on the number line, let's say I started here at the origin at 0, I would have to walk 1, 2, 3 spaces to get to this location. Right, so I have to go 3 steps to the right. Well, how many steps do I need to take to go to -3?
3 to the left.
Yeah. Going 3 spaces, 3 to the left. But notice that you didn't say I went -3 to the left. We're just talking about steps here. And we don't want to complicate our lives by thinking about negative steps, whatever that means. Maybe it'd be a step backwards or something. But it turns out that the sign, negative or positive, tells you something about the direction that you're going on the number line. And when two numbers are on the opposite side of the number line, we say that they have the same absolute value, because absolute value is a number's distance from 0. On the number line. And this is going to be an important concept, that distances from 0 are always positive. So distance is always a positive measurement. Well, you might be asking why. And I don't have like a super good explanation for why that is, but I have an analogy for you that might clarify some things. Think about if I were, measuring a wall, like the length of a wall, because I'm going to put trim on the floorboard, right? I'm going to put trim on the wall. I would measure, let's say I'm standing right here. Let's say maybe a different scenario. I want to measure my distance to this dog. This is my dog. Okay. And I want to measure that distance. Well, one thing I could do is get out a measuring tape and measure, extend that measuring tape out. And let's say that the dog is 8 feet away. Okay. Well, now I want to measure, let me see, I have a cat over here. This is my cat. And the cat is some distance away in the opposite direction. If I turned, I'm still in the same position and I still have the same measuring tape. If I turned in the direction of the cat to measure out how far the cat is from me, do negative numbers suddenly appear on my measuring tape?
No.
No. I would just say that the cat is in some different direction. Maybe the cat is 4 feet away from me. But the measurements I took, the measurement of distance, is always reported as a positive value. So mathematicians came up with this this symbol that will tell us the absolute value of a number. Okay, and the symbol that we use to describe absolute value, or a distance that a number is away from 0 on the number line, are these vertical bars. I'm going to put something like this. So there's a number that's placed inside these vertical bars. And those vertical bars indicate to you find the distance from 0 for this number x, whatever that number is. So if, for instance, I asked you, let me give you some examples, the absolute value of -8. Okay. find the absolute value of -8 or report back what is the absolute value of -8. Can anybody tell me what that distance from 0 is?
8.
8.
Yeah, you would just say 8. Positive 8. We would just drop the sign. Okay. If I asked you what the distance -102 is from 0, or the absolute value of -102.
102.
Good. If I asked you what is the absolute value of 33?
33.
33.
Okay, cool. Some students make the mistake of saying that the absolute value of 33 would be -33, but you have to remember that this is telling you whatever is inside the absolute value bars, spit out the positive distance from 0. It's always going to be positive. So if this number on the inside is negative, it'll spit out a positive. If it's positive, it'll still spit out a positive. Okay? So don't make the mistake of just saying switch the sign, because that's not what the absolute value is asking. And it turns out that this idea of absolute value is sometimes used to teach how to add numbers that have different signs. So for instance, I think in last week's lecture, we mentioned this briefly, adding numbers with opposite signs. Let's say that we had 10 plus -34. Well, there's a couple of ways you could tackle this. One way is that you could say, okay, if I have $10 and I have -$34 of debt, right? You could interpret it that way and say that I should have -$24 in total, right? But sometimes mathematicians or math teachers teach adding numbers that have different signs with this idea of absolute value. That if you're adding numbers with different signs, you're always going to look at their absolute values and ask yourself which one has a bigger absolute value. And you're going to take the number that has a bigger absolute value, which is 34, and because they're opposite signs, we're just going to subtract the other number, 10. So we're subtracting their absolute values. And we should get 24. But then we have to keep the sign of the larger absolute value. And the sign of the larger one was this negative. This negative number had a bigger absolute value. So really our answer here should be -24. It's sort of a complicated way to get to the answer, and there's a lot of ways to approach it, but that's one way that, like if you took Math 410, elementary algebra before this, they might have taught it in terms of if they're opposite signs and you're adding or subtracting, or if you're adding two numbers with opposite signs, find their absolute values, take the absolute value of the bigger one minus the absolute value of the smaller one, and then keep the sign of the bigger one. In my head, I like to think about, I mean, I do it quickly. I say, which one's bigger? I'm going to keep that sign. But that only applies to adding numbers with opposite signs. You don't want to overgeneralize that. You don't want to generalize it to multiplication and division, for instance. So the reason why I bring up absolute value is because you're going to see some algebraic expressions that have absolute values used as a grouping symbol. But it's a special kind of grouping symbol that once you simplify everything inside the absolute value bars, then you have to take the absolute value. So let's look at an example that has us simplify some stuff and then has absolute value in it. Okay, so Well, let me start us off easy. So absolute value practice. 1. What is the absolute value of -1?
1.
Yeah. What is the absolute value of -3/5?
3/5.
Yeah. 3/5. Good. And let's think about what is the absolute value of -5 plus 9?
4.
Anybody get any different answers? I'm not sure who said 4, but how did you walk me through how you got that?
I don't know. It just popped into my head.
Okay. Yeah. And sometimes it does. But sometimes you can't trust what pops into your head and you sort of have to know how to break it down. So let me show you how you would break it down. 4 is the correct answer. I didn't mean to give you any sort of stress or trepidation there. What you'll do is treat the absolute values as a grouping symbol. Absolute value is G for GEMDOS, right? So we need to do all of the operations inside the grouping symbol first. So think about it like the stuff in here is grouped together. So within this grouping symbol, I have to think about doing GEMDOS again for whatever operations are in here. Well, the only operation in here is addition. So I'm going to skip right to addition, and that'll be the first thing that I do. So -5 plus 9 should be +4. And then I haven't used the absolute value bars yet. I will evaluate the stuff inside the absolute value bars, and then I will take the absolute value. So the absolute value of 4 is then 4, and we can just call it a day there. Okay, now that might seem convoluted, but let me give you another example. Let's say I had -10 minus 12 inside my absolute value bars. What should this one be?
22.
Yeah, can you explain to me how you got that?
Add, -10 minus 12
Yeah,
is -22, and then put the bars.
yeah. And then you
And
take the
then
absolute
divide-
value.
Yes.
Yeah, perfect. Everybody get that? Anybody have any confusion still about that? Okay, we're gonna see some more absolute value stuff here in a little bit. Let me complicate your life a little bit more. You might have problems that say you have more complicated expressions. It might say let x equal 6 and y equal -8. Evaluate 4 times the absolute value of x plus 5 times the absolute value of y. And that's the way you got to read it. So if there's a number on the outside of the parentheses, or if there's a number on the outside of the absolute value bars, when I say it, when I read it out loud, I say 4 times whatever this is. So 4 times the absolute value of x plus 5 times the absolute value of y. Okay. And if they're asking us to evaluate it, then, and they've assigned these variable values, then what we need to do is substitute the values into the problem. So you might write the expression down the original expression, and then you might say, okay, well, I'm going to sub in these values. So I'm going to have 4 times the absolute value of something plus 5 times the absolute value of something. And then we'll just plug those somethings in. So this is x, so I'm going to plug it in right here. And this is y, so I'm going to plug that -8 there. So there's a 6 here. There's a -8 there. And now that I have a numerical expression instead of an algebraic expression, I can start to simplify this. I need to do my grouping symbols, exponents if I have them, multiplication, division, addition, subtraction. So I have some grouping symbols because I have absolute value. But there's nothing to do inside the absolute value, right? There's no operations on the inside of them. So I'll just take the absolute value of these two numbers. So I'm going to write down the 4 here plus 5 here. And where I had the absolute value of 6, now I'm going to just write times +6. And typically what I do is I just change the absolute value bars into parentheses and just multiply. Because to me, parentheses also indicates multiplication. So I'll just put parentheses here to indicate multiplication. And the absolute value of -8 is +8. So this, when I do the multiplication before the addition, so we're going to multiply, then add, I'll have 24 here plus 40 here. So I should have 64. And that should be my answer. Does anybody have any questions there? Questions, comments, or concerns? Okay, well, that's what some of the homework problems look like. So let me give you some more examples and we'll finish it up. Let's look at 18, which is in the workbook. But for our purposes, that was really number 6. And this one says we have this expression 4x plus 4 times 3 plus a, and that is squared. Let me call this a like this, all over y plus 1. And I'm going to throw absolute values in here for good measure. And we'll say here that x is equal to 2, y is equal to 3, and a is equal to -4. So we're just going to handle this using order of operations as opposed to simplifying it, because let's throw the numbers in and see what we're really working with. So what my recommendation is that for any time you have a variable, you put like you can either leave a space, but I like to use a parentheses. So what I would do for this 4x is I would write 4 times something plus 4 times 3 plus. And then since I already have parentheses here and I don't want to like double up on parentheses, I'll just leave a blank here, squared, all over something in absolute value plus 1. I'll put a little flag on the 1 just so we know it's not an absolute value bar. And then I'll plug in the values that I was given. So I have an x here, and x is 2. 2 there. 3 plus a is equal to, well, I'm going to put -4 here in parentheses just so that I don't like stack those operations on top of each other. Then y is 3, so I'm going to put the 3 here. Now, if you wanted to, you could rewrite this on the inside of the parentheses as 3 minus 4. It'd be a lot simpler. But in any case, we'll use our order of operations and do whatever's in the grouping symbols first. So I can take care of 3 plus -4 right off the bat. And I can take care of this 3 plus 1 right off the bat. So I might leave this as 4 times 2 plus 4 times 3 plus -4 should be -1. Now I'll throw the square up here, right there. All over the absolute value, 3 plus 1 is 4. And maybe it'd be a little bit less confusing if I put a little dash line here so you can see, you know, step 1, step 2, step 3. And I'm just slowly walking through the order of operations. You got to practice enough to pick up speed. We're going to go to, you know, you could call this absolute value of 4 is 4, so we can call that 4. But I'll go to the exponents now, and then just take -1 times -1. Well, that's going to be +1. So I can sub in, let's say absolute value of 4 is equal to 4. I'll sub in that this is 4 times 2 plus 4 times +1 now, all over 4. And I've taken the absolute value, so I no longer need the bars. Once you use that absolute value, you can drop the bars. I can take care of all of this stuff on top of the fraction bar if I wanted to. The multiplication has to come before the addition. So I might say that this is 4 times 2 is 8, plus 4 times 1 is 4, all over 4, which would be 12 over 4, which is equal to 3. Okay, so the only way that you're gonna like really get comfortable with this, you're not gonna learn this by watching me do this. The notes will be helpful, but the only way you're gonna get comfortable with this is by getting into the homework and doing it. So the stuff that we've covered so far in today's lecture, I'm gonna go ahead and cut us off now because I'm sure we've had enough for today. You're gonna get tons of practice in if you need to finish up homework for section R2, part 1. And then part 2 is open and it's the same kinds of problems, but just a step up in complexity. So there's going to be plenty of practice there. What I recommend is that you get in there as soon as you can, whenever you have some free time, just to take a look at them, do what you can. And then the more complicated things, if they're giving you, if it's taking you a while to figure out what you're even looking at, that's when you need to go to Math World or schedule an office visit with me so we can work through some of those things. Because in class, you know, I can't take too much time to do individual issues. Math World is where you get that assistance and my office hours, okay? So if you have any questions, you guys are free to go. You should be good for that. I'll see you guys on Wednesday. If you do have any questions, though, feel free to hang back and we'll talk about some things.
Thank you.
Thank
got
you.
it. Have a nice
Have
day.
a good day.
Yeah,
Thank you. Thank you. Have a good day.
you too.